So I'm Sawsan El Zahr. I'm a third-year PhD student at the University of Oxford, and today we'll talk to you about carbon-aware routing, the metrics and challenges. This work was a joint work with Paul Gunning from British Telecom, who's here, and my supervisor, Noah Zilberman. So to achieve net zero goals by 2050, we really have many initiatives. Most people focus on data centers where we have the computing, because one data center can report 10 to 20 terawatt hour per year, whereas for networks where we have the data transmission, an ISP reports 3 to 6 terawatt hour per year, which may seem less significant. However, because we have many more ISPs, these smaller contributions will sum up, and consequently, the carbon emissions of the network are not negligible. So let's start with a small network or small example. Here in the network, if we want to send a packet from router A to router E, we have two different paths. So previous works focused on increasing the energy efficiency, which is maybe by routing through the shortest path. However, different routers are located at different locations and consequently are fed from different energy sources, which means that they have a different carbon intensity. The carbon intensity is the indication of the greenness of the energy at every location. So in this example, it could be better now to route through the upper path instead of the lower one. So this adds the geographical dimension of the energy mix per region to the routing problem. And because this carbon intensity or this energy mix is predictable now per region thanks to new prediction algorithms, we can take benefit of this information, integrate it into routing, and see, well, how much can we save in terms of carbon emissions. So this work is specifically in the context of routing, and it addresses the operational carbon emissions of routers. So the first step is really to understand the building components of the carbon footprint. So it depends on the energy consumption and on the carbon intensity, the greenness of this energy. And I will talk about each of these separately. So first of all, if we want to measure the energy consumption of a router, we need a power model of routers. So a router, when idle, will consume some idle power, which is really significant. And then once it starts processing the traffic, it will have some dynamic power that is proportional with the utilization. Now, the idle power can be further divided into static power or zero-port power, in addition to the power to enable every port, and every port corresponds to a link in the network. On the other hand, the carbon intensity is the measure of how many grams of CO2 are released in the environment to produce 1 kilowatt hour of energy. So the unit is grams of CO2 per kilowatt hour. And this metric varies a lot per day, per season, per region. So in the figure, we can see the national carbon intensity in the UK for a day in different seasons. So this metric varies a lot, and we can see some significant changes just within a few hours, which means that while average values cannot be used, or they're not so accurate. Moreover, this carbon intensity can be forecasted up to 24 or even 48 hours ahead of time. And this was one of the main motivations for us to do this work, because now we can adapt the routing of the traffic ahead of time. We can plan for this ahead of time. So now, knowing that the carbon footprint depends on both the energy and the carbon, we came up with some energy-related metrics and carbon-related metrics to be integrated into the routing. So we need these metrics because we want them to be, we need some indications for the network to understand the energy and carbon aspects. So I will not go over too many details into the metrics, but we can have, for example, the typical power of routers, like some people in the morning were mentioning. We can have the energy rating of routers, and this one is like, well, it's good to have some energy rating metric of routers. Well, these are not standardized yet, but we came up with a definition, and it could be good to be shared between ISPs, for example. We have the incremental dynamic power per unit of traffic, and for carbon-related metrics, we can have the carbon intensity or the carbon emissions over the previous interval of time. And it's important to note that we can also have combinations of these metrics, so they're not just like one metric at a time. So to evaluate these metrics, we have two approaches. The first one is just a very simple one, change the link cost based on these metrics, apply the Dijkstra algorithm, and this will have an impact on the dynamic part because, well, still all the network are still on. So the next obvious step is actually to try to shut down some of the underutilized links or the unnecessary ports. So we came up with a carbon-aware traffic engineering heuristic that we denote by Kate. And what it does is, after changing the link costs, it also looks for the least utilized and highest carbon emissions links. It shuts them down for the specified period of time while keeping some redundancy in the network, because redundancy is important. And then it checks if the graph is still connected, checks the improvement, and so on. So this was a simulation-based study using the NS3 simulator. We applied it on different network topologies like British Telecom in the UK and the Giant Educational Network in Europe. And we also considered different traffic patterns. So for example, for the day traffic, we have mostly business customers, and traffic is more symmetric than in the evening when we have mostly downstreaming of video from caches to users. So moving on to some results. So here I only show some of the like the best metrics that we've seen, but you can check later the paper for more information on this. If we consider carbon-related metrics alone or energy-related metrics alone, the high savings is like 2 or 2.5%, but combined together we can have 4% carbon savings. And then for Kate, when we also further shut down some of the underutilized links, we can have up to 15% carbon savings and 7% energy savings. Now, it's important to note that these savings are only for the daytime traffic, because for evening traffic, these savings were really negligible. And this is because in the evening, when we have video streaming, the paths from caches to users are really short, because like CDNs and caches are located near users. So it's a bit hard to reroute traffic in this case. So carbon-aware routing may not be the solution for this case. Now, if we want to see the variation of the flow paths, here we see the flow intensity per region. So on the right, you can see the carbon intensity per region in the UK. So there are some open source websites that provide this information like every hour. And on the left, we see the flow intensity per region with OSPF compared to carbon-aware routing. So first, we can see that for Northwest England and East England, which are greener regions, we see that the flow intensity increased with carbon-aware routing. Whereas for East Midlands and South England, the flow intensity decreased, because these are like brown regions on the map. However, like for London, we see that the flow intensity was the same. So why is that? Because London has a lot of the nodes, and it's somehow like a bottleneck in the topology that we cannot route away from it. Another aspect from the simulation was to check the carbon savings when they change with the static and dynamic power ratio. So for example, chassis-based routers have a very high idle power, and for these ones, the ratio would be really high. So the carbon savings, if you see on the map, the higher the static power, the lower the savings. So it's so important to note that, well, it's very important to invest in replacing equipment with lower static power, because the static power, once it's there, you just can't do anything about it. So in summary, this work helped us understand the challenges and the metrics of carbon-aware routing. So carbon-aware routing has some potential benefits, like we've seen some 15% carbon savings, but it also has some challenges and bottlenecks. So in terms of metrics, the carbon intensity combined with the incremental dynamic power per unit of traffic was the best combination of metrics. In terms of challenges or bottlenecks, the high idle power presented like a really bottleneck, and it limits carbon savings. We also have the routing bottlenecks in the topology, like London in the UK, where we have most of the nodes. So it's a bit hard to, in the current topologies, to route away from London, but this is something to consider for future deployments. And finally, the carbon optimization is application specific, because we've seen some really good carbon savings for daytime traffic, but for evening traffic, when we have the downstreaming of video downstreaming, for example, the savings were really lower. So maybe carbon-aware routing is not the solution for these cases. So the code is, the NS3 code is available on GitHub, and the QR code is for the paper that was published in ACM Connext. And if you want to see a longer version of this talk, I previously gave a 25 minutes presentation on it in IETF 121. That is also on YouTube. Thank you.
Thank you very much. Do we have any questions? I know we have one remote.
Hello, Greg Choules, ISC. Thank you, very good talk. So far, are these just simulations of what you might be able to achieve?
Yes, yes.
Is there any thought, since you have presented at the IETF, is there any thought to actually making modifications, for example, additions to traffic engineering protocols to allow for the incorporation of the extra metrics?
Yeah, so in the IETF, we have the time variant routing working group, and these are looking for metrics, and the carbon-aware routing is more like a use case of this in this working group. So yeah, they are looking at these things, yeah.
Okay, and sorry, second point, might, as well as being able to shut down ports, inactive ports, have you considered that you might be able to shut down entire routers?
So here because like for every point of presence, you still have some local traffic to route. So if you want to shut down the routers, it's a bit hard. So we didn't consider this. So we only looked at ports, but it could be one option. But yeah.
Thank you.
Thank you.
Hi, Stefan Funke from Interlink. We care about sustainability as well. One question I have is, when you simulated this with BT, did you look at latencies when you turned or switched the path for carbon net neutrality or saving energy? So do you have a comparison of when you shut down a link which is basically not used, traffic gets rerouted, did you look at the consequences and latencies, because that's what most of the customers are looking for?
Yeah, so we looked at the latency. It didn't increase much, and it's like for path stretching, it was increased by around 5%. But here I think I have some backup slides, maybe. Okay. Just. Okay, sorry. I think it's the last. Yeah, too many backup slides. But yeah, this is for Giant, and we see that the end-to-end path delay was really, it's the same with OSPF, so not much.
Cool. That's a nice selling point then, right? Because customers care about those things. Thank you.
Thank you.
Okay, and we have one question from the Slack from James Blessing, who asks, did you think about investigating the carbon costs of moving to a more regional peering strategy or local traffic handover?
Sorry, I didn't get the question.
Did you think about investigating the carbon costs of moving to a more regional peering strategy or local traffic handover?
So we looked at, so I still didn't get the question. Because we are looking at the scope 2 carbon emissions, so when we change the routing, so I'm not sure the carbon cost of what?
Moving to more regional peering strategy or local traffic handover?
No.
No.
Okay.
Any more questions? Thank you very much.
Thank you.
Interesting talk.